Good morning, everybody. First off, I'd like to apologize for not being there in person. My wife and I are actually expecting our first baby in a matter of days, and so I fear that if I made the trip across the country, I would probably end up with a longer hospital stay than she's going to have. So again, my apologies. Now we'll get back to the project. Today I'm going to be talking about the modeling approach and technical issues related to the development of the Wet Areas Map. What we see here, this is the provincially mapped water features as they exist across the landscape currently. This is all the water that's known about. This is all the water that can be managed against. This is the LiDAR-derived wet areas map for the same area. This particular example is in the boreal forest of Alberta, and we all know that there's a lot of water in that area. So having the predicted wet areas map really gives you a much greater understanding of the flows that you could potentially run into in the landscape. Now we'll just talk a little bit about the concept of wet areas mapping. So what we see here is just an ortho image, a 3D representation for reference. What we see here, this is the full feature LiDAR data. So we can see all the trees, we can see all the low vegetation, we can see all the roads, we can see all the clear cuts. With these features all removed, this is the bare earth LiDAR DEM. This is the main input driver to the predictive wet areas maps. The next step in the process is to predict the locations that we would expect open water channelized flow across the landscape. So what you see here is just a simple vector representation of the predicted stream channels for this area. Next, we assign a cartographic depth to water, or wet areas index, based off of these assumed open water features, based off of the topography surrounding each of these water features. Now, in general, we only tend to show the colors of the wet areas from dark blue to light blue, but we have to remember that there are actual depth to water values for every single 1 meter cell across this landscape. Now we'll talk a little bit about the data inputs in more detail. So what you see here on the left-hand side is the full feature LiDAR data set. It essentially looks like a grayscale image. This data captures trees, buildings, bridges. All these features are great for other uses, but they do inhibit the proper modeling of hydrographic flow or overland flow across the landscape, and as such they must be removed. Once they're removed, this is the bare earth LiDAR surface for the exact same area. So it's amazing the amount of detail and the amount of resolution and precision at which we can actually virtually deforest or clear cut this entire landscape. So to do this, software is used to classify the LiDAR returns, and only the likely bare ground returns are used to create this surface. This is hugely important for the overland flow routing in modeling that we do, which is one of the main steps within the wet areas mapping project. But there is one more step. Laser pulses or LiDAR pulses are not X-ray pulses. The roads act as an artificial dam, even though we know in our minds that there's actually a culvert in this location. But since the LiDAR pulse can't see that there's a culvert beneath the road, this road will simply dam up the flow unless we treat it properly. So breaches must be enforced across this obstruction. One way to do this is with culvert information. When map culverts are provided to us, we can integrate those. However, when they're not, algorithms have been developed to determine the appropriate length and angle of a virtual culvert to breach this road. In order to do the breach, DEM elevation values are reduced along the line to allow the flow across the road. Doing this, flow network connectivity can be maintained, and subsequently, wet areas are able to properly pass through the culvert. So as you can see in this slide, water does flow underneath the road. Water still pools on one side, which is actually what does occur on the landscape, but water still is able to flow unhindered across the road. So a little bit of summary about that. The bare earth LiDAR surface is the high resolution elevation information with fairly accurate bare earth data, which is the input driver to the wet areas mapping product. Roads can act as artificial dams when not treated properly. Mapped culvert data allows for proper road breaching, which improves the accuracy of the product. One of the outputs of the wet areas mapping data set is the predicted stream channels. These are used within the model to determine the basic flow network. They use a combination of single and multiple flow direction algorithms depending on the resolution of the elevation information. For this project, we've used a 4-hectare specific catchment area as a stream channel initiation. And I'll be talking a bit more about that as we progress. The primary outputs to the wet areas mapping project are the predicted stream channels, which are an intermediate output used within the model to determine the basic flow network. One of the other main product is the predicted wet areas map, which is cartographic or map-based. It is driven purely by topography with no input of soil and climate data. In terms of visualization of the wet areas maps, we tend to visualize these maps in shades of blue, from dark blue being more wet to light blue being less wet. The symbology can be altered to suit the user's needs. Different colors or different value ranges can easily be applied to this data. So what you see here is we have our zones of potential wetness, our wet areas maps. But a wet areas map can be flipped on its head and show zones of potential dryness. So a model that predicts wetness conversely also predicts dryness. It's the exact same mapped information, only symbolized differently to come up with a very different product. Some of the potential uses for dry areas mapping are in potential habitat mapping, locating potential sites of historical settlements, fire fuel loading, soil erosion and disturbance potential, and trafficability modeling. When we combine the wet and dry areas maps, we get a lot better representation of the predicted soil moisture gradients across the landscape. Now a little bit more about wet areas mapping specific to this project in the province of Alberta. The initiative started in 2004 as a partnership between academia, government, and the forest industry. Funding is currently secure to map 25.8 million hectares by 2015. This project is not only large in scope, but also large in terms of data requirements. The product is developed based off of bare earth LiDAR DEMs at 1 meter resolution and have been field verified to be accurate plus or minus 10 meters 70% of the time. This accuracy statement is delivered in the metadata and does tend to be fairly widely accepted by the end users. It is very difficult, however, to develop a pure accuracy assessment across such a large area. So we will say that the data tends to be more accurate as you approach the stream channels. In terms of data requirements, for the area that has currently been delivered, as you see in green, the input data weighed in at 815 gigabytes, and the output data was approximately 9.5 terabytes. So it's a very, very large project. In terms of the data outputs, the main output would be the wet areas mapping data, which you see here on the left, which identifies the predicted depth of the saturated surface layer based off of the expected normal seasonal average. From the initial DEM, we derive the flow direction raster, which identifies the direction of flow from each cell to its steepest downslope neighbor. And from this flow direction raster, we're able to identify the accumulation of flow from each cell towards each downslope neighbor. So the flow direction and flow accumulation rasters are used as input to the wet areas mapping final product. Some of the uses of the wet areas maps to date, just kind of a broad overview. What you see here is a representation of mapped water features. So all of the provincially mapped features are currently turned on in this image, and all we can see is a stream that runs north-south. This is the predicted connectivity based off of the wet areas map for the same area. So depending on a final user's needs, whether it be infrastructure placement, where to put the roads, or whether it's someone who's interested in information from a conservation perspective, where you might look for salamanders or different rare or invasive species, this map can prove very, very valuable. One of the other uses tends to be in road and infrastructure placement. The proper placement of roads can greatly reduce the cost of the road in terms of backfilling the roads, in terms of the requirement for the number of culverts and the maintenance on these culverts. So having the wet areas mapping data before you start to look at your infrastructure placement can really start to save you money. Another one of the uses that we'll look at here, this is an example of hydropole infrastructure placement. So what you see in red is just the outline of an area that we're going to be zooming into. So now what you see is that zoomed profile, and the small green triangles represent the actual locations of hydropoles along this transect. As we look at this profile in more detail, we can start to see the hydropoles as green triangles on the top image. Now when we look at the profile on the bottom, we can start to see the purple profile shows the bare earth elevation, which actually captures with fairly good detail the height of each of these poles, and if not the height, at least the location. And what we see at the bottom is the profile of the predicted depth of water values as we transect this corridor. Now we're just going to zoom in specifically on the hydropole with the little red arrow there. When we start to look at the hydropole in the center, we can start to look at its proximity to a predicted wet area. In terms of frost heaving or pad placement, we can start to see that if this pad were moved potentially 5 meters to the north or to the west, that we might have reduced the need for further maintenance. So having this information in the planning process can be very valuable. Now a little bit about the data formats. The native output of the wet areas mapping product is delivered as a floating point ESRI raster, which is the native format for ESRI's ArcGIS and ArcMap software. For this data, there is one floating point or decimal value for every 1 square meter cell across the landscape. So here we can see a conceptual example of a small subsection of wet areas raster data. So you can see that each cell contains decimal precision information in terms of the predicted depth of saturated layer. We can symbolize this data with shades of blue, or whatever the end user decides, to come up with the final depth of water visualization. Now for this data type, the cell values remain unchanged, but any variety of symbology can be applied to visualize these maps. The data layers maintain their maximum fidelity, so they can be quite large. This format is best for use with additional ArcGIS or GIS analyses, or as input into additional planning models. One of the other delivery types for the wet areas mapping data is a color map geotiff, which is easily read by all current GIS software and image editors. For this data format, one integer or non-decimal wetness code is applied for every single 1 meter cell across the landscape. So as you can see in this conceptual example, we have the same location, only instead of the actual decimal precision depths of wet area, we have the wetness codes. And with the geotiff, there is an internal symbology which is locked to the data, which allows for it to be symbolized as before. Only in this situation, this symbology cannot really be changed. We don't know any information about the actual depth or the depth to water outside of these predefined wetness classes. For this data type, cell values are changed into wetness classes and an internal symbology is locked in order to visualize the maps in a predetermined way. The main benefit of this data set is the drastically smaller file size. 1 gigabyte of raw floating point data can easily be compressed down to 10 megabytes of output geotiff. This is the best format for visualizing the data quickly and efficiently, in terms of if you have to put this information on a laptop or a tablet or a handheld GPS unit. This would definitely be the format to be looked at. Now when we started this project, we had to decide on the trade-offs between resolution, fidelity, and speed. Processing at 1 meter resolution was a very large undertaking, but we decided to do that in terms of maximizing the quality of the output and utilizing the input LiDAR to its fullest potential. The idea of downsampling 1 meter LiDAR to 2 meters is a 4-fold loss in fidelity and accuracy. So now we're just going to look at a little bit of a kind of a conceptual overview in terms of data storage requirements based off of these simple resolution standards. So we can see going from 100 square meters for a cell size to 1 meter cell size, we change from 1 cell to 100 cells. We can see that the file storage requirements go from 0.34 of a megabyte to 34 megabytes. So you can start to see that as we scale this to the entire project of 25 million hectares at 1 meter resolution, file sizes become increasingly large. But this was done at the expense of maintaining the high accuracy, even though it would take longer to do this processing. Now, to try to make this an efficient project, we've actually been in contact with main developers at ESRI, at Last Tools, and many other developers in the industry to try to come up with methods that are both efficient and cost-effective. In terms of the methods that we do use to process this data, all of the LiDAR data sits on an internal server at UNB. When an area is set to be processed, information is sent to a computer, the wet areas maps are processed, and results are sent back to the server. In order to make this project scalable, we split the project across multiple cores and span it across multiple systems. In this way, we're able to do very large areas at high resolution with a fairly quick turnaround time. Now we're just going to show a little bit of an overview of a visual geographic representation of the LiDAR data and the processing as it occurs. Data is delivered to us from the Resource Information Management branch of ESRD as small subtiles. They're roughly 2 by 2.3 kilometers. Now of these, we merge 48 of these subtiles into quadrants or quarters of a 1 to 50,000 NTS tile sheet. So each of the processing units at which we deliver the wet areas mapping data are roughly 225 square kilometers. So what you see here, this is the final processing tile of bare earth elevation for this particular sample area. So once these tiles are all merged, they're sent back to the server until we're ready to start the wet areas mapping process. At execution time, the tiles are sent from the server back to a workstation and assigned one of the multiple processing cores. As we process, the edges of each of these LiDAR tiles are expanded as to maintain proper flow, overland flow across the landscape and reduce edge artifacts. If we process each tile as an individual island, we don't really have any idea of the contributing area outside of that particular LiDAR tile. So it's very important that we expand these edges. Once the processing is done, all outputs are clipped back to the original tile boundaries for both the predicted streams and the wet areas, and the final output is copied back to the server, the core is released, and we continue on to the next tile. This process continues as we iterate through all remaining tiles until the project is complete. The wet areas maps are a model. They're a modeled output based off of high-resolution LiDAR data. As such, a model comes with its certain assumptions. For this model, we make the following assumptions. We assume that overland flow is the dominant driver of soil moisture across the landscape. We have no requirement for soil texture information, bedrock geology, climate, or precipitation information. We also assume that the LiDAR data is accurate, since we rely entirely on the bare ground LiDAR DEM. Certain limitations do exist with the bare earth LiDAR elevation information, and I'll be talking about those in upcoming slides. We also assume a specific catchment area or contributing area of 4 hectares, and we assume that this is on average a good estimation of channel initiation from the perspective of hydrologic risk. We also understand, and it should be noted, that these headwaters or low catchment areas are often very small ephemeral draws. They're not always evident in the field because of the seasonality of these maps. So if you go in the late summer, you might not find an actual channel. You will very likely not find running water many times of the year at the initiation of these stream channels. But from a hydrological risk perspective, they are important. With the model, there are also certain limitations, and we're aware of these limitations, and I'll just kind of talk about some of those right now. Watercourse crossing enforcement is required for proper overland flow routing. As mentioned earlier, the roads can act as dams, and these have to be overcome. So when GPS crossing information is incomplete, we have to come up with certain intelligence in order to determine where culverts should exist. As we can see here, we have 2 mapped culverts in this particular sample area, which will help in terms of understanding the proper flow. But we can see this area in the south. We can see that there's a channel that runs up to the road, but we're not really sure if the channel does cross the road, if there is actually a culvert there or not. Now, without a culvert in that location, if we have a very small wet area, under 4 hectares of contributing area, on the upside of that road, that actually won't be captured within the wet areas mapping project. So that's one of the limitations associated with not having proper culvert information and accurate intelligence that can actually reach these roads. One of the other limitations is that oftentimes the predicted stream channels yield straight lines through lakes. Essentially, there is no information that would be properly available to define the actual stream channel location through a lake. So we artificially, arbitrarily define a connection just in order to maintain proper flow network connectivity. One of the other substantial limitations of the wet areas mapping project is that the bare earth digital elevation models are not always representative of the actual bare earth. LiDAR bare earth data is derived as a subset of last returns of laser pulses. And as such, if the last returns don't hit the ground, then we're not able to determine an accurate bare ground representation. So as you can see in these 3 circles in this bottom image, these peat bogs yield a false bare earth surface because the dense mat of peat doesn't allow for the proper penetration to the organic layer. There are also some potential artifacts in terms of slash piles or wind throw. As you can see here, we have a cut block that has occurred. You can see it evident on the ortho image on the left. And we can see some artifacts along that western edge in the bare earth LiDAR. That is actually not representative of the actual bare ground locations within that cut block, but it's likely that wind throw and things like that have actually caused this misclassification of bare ground LiDAR data. One of the other limitations of this product is that we make no claim to the actual classification of wetlands. We are only here to define the extent of wet features to help identify the productive land base. As mentioned earlier, the raised bogs or raised peat bogs initially did prove problematic, but solutions have been developed to overcome this issue. In terms of the wetland extraction algorithm implementation, research does continue, and it is actually the focus of my master's thesis currently. The data has been delivered so far in 2 main phases. Phase 1 was in the south, and Phase 2, which is in kind of the central area that you just see there. For Phase 1, no bog algorithm extraction was implemented within the delivery, so that's something to take note of. In Phase 2, and in all subsequent phases, the bog extraction algorithms will be implemented prior to delivery. With that, I'd like to thank you for your kind attention. And before I do, I'd just like to say thank you to ESRD's Forest Management Branch and Resource Information Management Branch for the seamless communication on this project. Without these 2 groups, this project would not be possible. And so thank you very much.